talk about the most important topic of integration, the fundamental theorem of integral calculus. We start from the mean value theorem, then we define the integral function, and finally we prove the fundamental theorem of integral calculus. Now, Maggi, go through the graph.
Today we are going to talk about the mean value theorem. I'm going to write this formula, which is our function that goes from the compact A and B to R. Our function has to be continuous in our compacts A and B. So, it has to exist C belonging to our compact A, B, so that the integral between A and B of our function has to be equal to B minus A multiplied for a function of C. So, geometrically, if the function is positive in A and B, the mean value theorem expresses the equivalences between a trapezoid, which area has to be integral between A and B of our function in the x, and a rectangle. Their base has to be equal to B minus A. The height is given by the f value in a particular point of our range AB. This point is called C. The function of C is equal to the integral of our function on the base of the rectangle and the trapezoid, which is B minus A, which is the median value of the height of the trapezoid. Graphically, the area of this trapezoid is ABCD, is the area of the rectangle ABEF, which has for its base the segment B minus A, and for its height the function f of C. What you have to know about the mean value theorem. Thank you.
F is an application that goes from the compact AB to R. F must be continuous in the interval AB. F of x is an integral function if and only if for every x belonging to the interval AB appears that f dx is equal to the integral defined between a and x of f dt in the t. Now let's see the geometric meaning of the integral. F dx is a function of the extreme top of the integration interval. Now let's see the geometric meaning of the integral function. Let's go on the Cartesian plane and we draw our function. And on the horizontal axis we mark the interval AB and draw the parallel of the ordinates axis. Take a point x within interval AB AB. Also the trace of it, the parallel to the y-axis. It is to form a trapezoid of vertices A, B, C, D. F of x represents the area of the trapezoid, and this area depends on the value of x variable in AB.
Thank you.
Sorry, it is A and B.
Thank you.
Fundamental theorem of integral calculus, known as Torricelli calculus. F is a function or application that goes from the compact AB to R, and F is continuous in the compact AB. Then we will say that f of x is equal to the integral between a and x of f of t in dt. It follows that for each x belonging to the compact AB exists a first function of x such that the first function of x is equal to f of x. That is to say that the derivative of the integral function is equal to the value of the integral at the point considered. That means is a primitive of function. We show the graphic. We consider x and x plus h belonging to the compact AB with h different from 0 increasing the variable x. R f of x is equal to the integral between a and x of f of t in dt, and f of x plus h is equal to the integral between a and x plus h of f of t in dt. So we calculate the increase of the function. This is equal f of x plus h minus f of x. This is equal integral between a and x plus h of f of t in dt minus integral between a and x of f of t in dt. Applying properties of integral that we have, this is equal to integral between a and x of f of t in dt plus integral between x and x plus h of f of t in dt minus integral between a and x of f of t in dt. These are opposite and go away. This is equal the integral between the x and x plus h of f of t in dt. These are the increase of the function. For the mean value theorem, then exists at last one point C belonging to the compact x and x plus h. This is equal to f of c by h. So we write f of x plus h minus f of x is equal to f of c by h. We divide both term by h, so we have f of x plus h minus f of x on h is equal to f of c. Passing to the limit, 0, C, who belonging to the compact x and x plus h tends to x. So we have the limit as h approaches 0 of f of x plus h minus f of x on h is equal to the limit as c approaches x of f of c. The function is differentiable, so we have the first function of x is equal f of x, as we wanted to prove.
The formula of Newton limits is the formula for calculating the definite integral. If we have f of x and g of x that are the primitives of the function f of c, which goes from the compact AB to R, and the function has to be continuous in AB, and the primitives differs each other for a constant, so that f of x is equal to g of x plus c. We can say that the integral from a to x of the f of t in the t is equal to g of x plus c. If we say that x is equal to a, the integral from a to a of the f of x in the x is equal to g of a plus c. But we know that the integral in the same point is equal to 0. So g of a plus c is equal to 0, and c is equal to g of a. So the interval between a and x of the f of t in the t is equal to g of x minus g of a. If x is equal to b, the integral between a and b of the f of x in the x is equal to g of b minus g of a. But we know that g of b minus g of a is equal to the definite integral between a and b of the g of x. The formula that we found allows us to calculate, to bring the calculator of the definite integral into the calculator of the indefinite integral.